Okay, so in the next part of this lecture, we will discuss about the rotation of rigid bodies. So this is more about the rotational motion. So far, we were discussing about uh, the linear motion. That is when the body was moving in a straight line or in a curve. But now we will discuss about the rotation of rigid bodies. Okay, so in this part of the lecture, we will discuss about the rotation of rigid bodies, and then we will discuss about angular displacement, angular velocity, and angular acceleration. Uh, and then similar to the constant acceleration equation in linear motion, we will also discuss about rotation with constant angular acceleration. And we will also discuss about relating linear and angular kinematics. And then we will discuss about kinetic energy in rotational motion, and about moment of inertia. We will introduce moment of inertia here, and then we will discuss how we will calculate the moment of inertia using the integration procedure. And we will discuss about parallel axis theorem, which is a way to calculate the moment of inertia. And these final two topics will be discussed in the next lecture. Okay, so as far as the rotation of rigid bodies is concerned, so in analyzing rotational motion, so let's think first about a rigid body that rotate about a fixed axis. So if you consider a body here, uh, for example, if this is our x axis and y axis, and if we consider, for example, a body here, and this body is rotating about this fixed axis O. So figures show a rigid body rotating about a fixed axis, which is O here. The axis passes through point O and is perpendicular to the plane of the diagram, which we will call is XY plane. And one way to describe the rotation of this body would be to choose a particular point P. So for example, we will choose a point P here, and then we will track the x and y component of P. So this way we will describe the motion of this body here. But this isn't very convenient since it takes two number. That is, you need to track of both x and y position of particle P. So now there is the angle theta that OP makes with the positive x-axis, as you can see here. So this is the angle theta which this OP make with the positive x-axis, is a single angular coordinate that completely describe the body rotational position. So instead of two coordinate x and y, we will just use only one theta, and as the distance of P from O is not changing, so therefore only theta is enough to describe its motion. Now the angular coordinate theta of a rigid body rotating around a fixed axis can be positive or negative. Now it's totally depend on our own choice. If we choose a positive angle to be measured counterclockwise, as in this case, if we choose this is our positive angle, uh, then the angle theta in figure is positive. But if you choose your positive to be clockwise, then this angle will be a negative angle. Okay, so now how we will measure this angle? We can either use radian, or we can use degrees. But as you can see in this figure here, so if we consider this rigid body motion, so if we take this as our R, and if this is our S, which is this S here, which is the length of this arc along this circle. So if this S is equal to R, then this angle this angle is what we call is a 1 radian. So therefore, what we will say here that the most natural way to measure the angle theta is not degrees, but in radians. As you can see in this figure, that 1 radian is the angle subtended at the center of a circle by an arc with a length equal to the radius of the circle. Now, again, if you want to calculate this S here, and if you know this R, so this S will be equal to R theta. And if this is our theta here, and if you want to calculate theta, so theta will be equal to S divided by R. So in figure, which is this is our 9.2a, and this is figure 9.2b. So in figure 9.2b, an angle theta is subtended by an arc of length S on a circle of radius r. The value of theta in radian is equal to S divided by R. So the value that you will get here should be in the radians. Now the circumference of a circle, which is this this whole arc around the circle, that is the arc length all the way around the circle, is 2 pi times the radius. So this means that the so there are 2 pi about 6.283 radian in one complete revolution, which is 360 degrees. So therefore we can write that 1 radian is equal to 360 divided by 2 pi, which is about 57.3 degrees. So 1 radian is about 57.3 degrees here. Okay, so the S, which is you can say is the distance here along the circle, and theta is the angle here. Okay, now based on this, now we can also define angular velocity. So angular displacement is theta, but now we want to calculate the angular velocity. So the coordinate theta specify the rotational position of rigid body at a given instant. So for example, if you consider again the same figure, and assume that the body was initially here, and the angle here was theta 1, and then at another time, so the time here was t1 here, and then it equal t2. The same body then moved to this another position, and this angle is now theta 2. Okay, so a reference line OP is rotating rotating body makes an angle theta 1 with the positive x-axis at time t1, which is this angle, and we can call this line is OP. And then at a later time t2, the angle has changed to theta 2 now. So we define the average angular velocity, which is you can represent by this letter here. So if you call this is our x-axis, this is our y-axis, so then the z-axis is out of the plane of this paper, and therefore we will represent the velocity, angular velocity, by omega average z. So this is average angular velocity, and about the z-axis, because the body is rotating about the about the z-axis here, in the time interval delta t. So the time interval here is from t2 minus t1 is the time taken when the particle moved from this position to this position here. So the angular velocity, the average angular velocity, will be the delta theta, which is the angular displacement. So the final angular displacement minus the initial one will give you the delta theta. So if you divide, so if you want to calculate this average angular velocity, it will be just simple is theta2 minus theta1 divided by t2 minus t1. You can write this delta theta divided by delta t. So this is how you will represent the angular velocity here, which is the angular displacement divided by the time. And the subscript z here, as you can see, this z indicate that the body is rotating about the z-axis, which is perpendicular to the plane of the diagram. The instantaneous angular velocity, so this is the average angular velocity, but we are also interested to calculate the instantaneous angular velocity here, which we will represent by just omega z, is the limit of when this average angular velocity is delta t approaches 0. So if you want to calculate the omega z here, so we will just write that limit when delta t approaches 0 and delta theta divided by delta t. And now we know that this is the definition of a derivative. So simply you can write this is d theta divided by dt. So the omega z, which is the instantaneous angular velocity, is just the derivative of the theta with respect to time here. Now the angular velocity, which is the average angular velocity, which is this thing here. Now can be positive or can be negative, depending on the direction in which the rigid body is rotating here. So in this case, if we uh, if we consider that the angle is positive in this direction, so if this is our positive angle, and in this case the body is rotating in this direction here, so the theta is increasing here, so angular velocity is positive. That's why the angular velocity is greater than 0. So we can say that omega az minus z, which is delta theta divided by delta t, is greater than 0. Now delta t is always positive, but in this case, because the angle is increasing, so this means that the final angle uh, is greater than the initial angle, and then delta theta will be positive. So the average angular velocity is positive in this case. But in this case, because the body is rotating in the clockwise direction and the angle is decreasing here, this means that theta2 will be smaller than theta1. So then delta theta will be negative, and therefore the average angular velocity is negative in this case here. Now, in case of instantaneous angular velocity, which is omega z, the direction of omega z can be calculated using the right hand rule, as you can see in this figure here. So if you curl your finger in the direction of rotation, so in this case, the body is rotating in this direction here, in the counterclockwise direction. So if you curl your finger in the direction of the rotation, your thumb will point in the direction of the angular velocity. So the direction of angular velocity in this case is in the upward direction. In this case, because the body is rotating clockwise, so if you curl your finger of the right hand rule in the direction of the rotation, your thumb will point in the downward direction, which is the direction of the velocity here. Okay, now which velocity is positive, this one or this one? So it again depend uh, on this case here. So in this case, because this is our x, this is our y, and this is our z. So in this case, because the instantaneous angular velocity is pointing in the positive z direction, so therefore it's positive. And this one is pointing in the negative z direction. So this means that it's a negative angular velocity. Okay, so now we can also introduce angular acceleration here. So if you consider this body here, so initially it may be moving with some angular velocity omega 1 z, and then the second angular velocity after time t. So this is time t equal t1, and this is t equal t2, and then this will be maybe omega 2z. So this was the initial angular velocity of this body. which is rotating about this point here, and this is the final angular velocity of the same body. Uh, so f omega 1z and omega 2z are the instantaneous angular velocity at time t1 and t2. We define the average angular acceleration, which is this we will represent by alpha average z over the interval delta t, which is t2 minus t1, is the change in angular velocity divided by delta t. So this alpha, which is the average angular velocity about the z-axis, will be equal to omega 2z minus omega 1z divided by t2 minus t1. And now this the term on the nominator is just the change in velocity, the change in angular velocity, which is we can represent by delta omega z, and then this is change in time, so which is you can represent by delta t. So this means that the average angular acceleration is equal to the average angular uh, so which is equal to the change in velocity divided by the change in time. Now the instantaneous angular acceleration, which you can represent by alpha z, is the limit of this average angular acceleration when the delta t is approaching zero. So if you want to write the equation for alpha z, so alpha z will be equal to limit when delta t is approaching zero, delta omega z divided by delta t. And again, this is the definition of the derivative, so which is d omega z divided by d t. So this means that we can write the instantaneous angular acceleration, just the derivative of the omega z with respect to time. Now the usual unit of angular acceleration is radian per second per second, uh, and also we can write that alpha z is d omega z divided by dt. So you can also write this d by dt, and because omega here is d theta divided by dt, so which you can write is d square theta divided by dt square. Okay, now angular acceleration again can be positive or negative. So if the angular acceleration is positive, then the angular velocity is increasing. And if angular acceleration is negative, then omega z is decreasing. So as you can see in this figure here, so in this case, the body is rotating counterclockwise. So the angular velocity is in this direction here, according to the right hand rule. So in this case, the angular acceleration is in the direction of the velocity here. So this means that the velocity is increasing here. The angular velocity is increasing. And in this case, the angular velocity is again in the upward direction, but the angular acceleration is in the downward direction. So this means that the angular velocity is decreasing with time. Okay, so alpha z is in the same direction as omega z if rotation is speeding up, and opposite to omega z if the rotation is slowing down. Okay, so now we can derive the equation for angular velocity and angular position by using the same procedure that we use for the straight line, which is rectilinear motion. So if we replace x with theta, vx with omega z, and ax with alpha z, then we can derive the equation for the angular motion. Now, if you remember these equation, that if acceleration is constant, then we can simply write these equations, these three very known equations that we used in the first lecture. So we can write similar equation for the angular motion by just changing x with theta, vx with omega z, and ax with alpha z. So in this case, as you can see, ax is constant. Now now if alpha z is constant, if alpha z is constant, then we can also write equations for the angular motion like these equations. So if we just change the v, so this first equation will become equal to omega z equal to omega naught z plus alpha z and t. So here we are just we just replace just bx by omega z and ax by az, and time will just stay the same. And similarly here, we will replace theta here, and that will be theta naught plus omega naught zt and plus half alpha zt square. And similarly for the final case, we will have omega z square equal to omega naught z square plus 2 alpha z, and then theta minus theta naught. So similar to these equation, we have a corresponding equation for the angular motion. So these are equation for the uh, straight line motion with constant linear acceleration, and this is a fixed axis rotation with constant angular acceleration. So in this case, you can use these equations here. Okay, so now we can try to solve this example here. And this example is again based on the angular motion, but with constant az. So again, we have these three equations here, which we can use in this case. Now, if you read the description, so you have finished. So you have finished watching a movie on a Blu-ray, and the disc is slowing to stop. The disc angular velocity at t equals 0 is 27.5 radian per second. This means that omega naught. So omega naught is 27.5 radian per second. And its angular acceleration is constant, which is minus 10 radian per second square. So you can say alpha z, which is minus 10 radian per second square. And a line PQ, which is this line here, uh, on the disk surface lies horizontal, lies along the plus x-axis at theta equals 0. So at t equals 0, so when time equals 0, this PQ is on this position here. So now what you need to calculate, what is the disk angular velocity at t equal to this? You need to calculate the angular velocity at t equal 0.3 angular velocities. You need to calculate omega z. And uh, what angle does the line PQ makes with the positive x-axis at this time? And in part B, you need to calculate at t equal 0.3. What you need to calculate? You need to calculate uh, theta here. Okay, so in the first part, yes, in the first part, what you need to calculate, you will be just using this equation here, the first equation. So this equation here, so which is omega z. So omega naught z and plus alpha z t. So you are given omega naught z, which is this value here. You are given time, which is 0.3. You are given alpha z, which is minus 10. So you just need to calculate omega z. So 27.5 and minus 10 into 0.3. So from here you can calculate the omega z, which is 24.5 radian per second. So you calculated the final angular velocity, which is less than the initial angular velocity, which is this value here. And because the acceleration is negative, okay, so finally we need to calculate theta here. So for the theta, maybe we will use this equation here. So okay, so theta equal theta naught is 0, omega naught z t plus half alpha z t square. Now this thing is 0, so theta will become equal to, so omega naught, which is 27.5 and zero point 0.3 plus half alpha z, which is again minus 10 and 0.3 square. So now from here we can calculate theta, which is 7.8 radian. So you can also convert this into revolution. So theta will become 7.8 divided by 2 pi, so which will become 1.24 revolution. And you can also change this to degrees. So this will become equal to uh, 1 revolution. So if you just uh, 1 revolution is equal to 360 degrees and plus 0.24 into 360. So then it will become 87 degree and plus 360 degrees. So you will get this answer from here. So the procedure of angular motion is very similar to the procedure of the linear motion.